All right, welcome. Now, tutorials are a little bit different, and they're a little bit the same. With a lecture, I have pretty much a set agenda. I got to cover this amount of material. If the class gets extremely confused, only then do I tend to slow down. For a tutorial, what does a Friday afternoon mean? There's no other better time to do physics. Gives us a time to slow down. I did hear your eyes roll a little bit. I heard that. And it's a time for us to discuss things. It's a time for us to explore things. To the people watching and to you guys, you guys have never done physics before, and I understand that. And so one of the things that we do is we take a look at the homework that's assigned, we explore it, we basically do it, and you guys need to sit, watch, learn, and ask questions, tons and tons of questions. If you don't understand anything, I can guarantee someone else in the room doesn't understand as well. I don't mind doing homework. If I had it my way, the homework would be worth nothing. But what would that mean? That would mean you wouldn't do it, which means that you wouldn't be prepared for the tests, which means it would just be a disaster. So I have to make it worth something to keep you guys honest. We'll talk about how the homework is graded later. And those are all the announcements. So, what do you guys want to talk about? We work together on this, so lead me, ask. Well, looks like we all understand physics. Let's call it a day. No, something must mystify you. Let's kind of look at problems 1 through 6. Who has really difficulties with number 1? All right, we all got it. Now, one of the things I will say this about tutorial is I won't give you the numbers. What I'm going to do is I'm going to show you the procedure, get right up to the point where you go, now compute it on your calculator, and then you guys could figure it out. If you guys can't get it right with your calculator, well, that's your problem, figure it out. So of problems 1 through 6, which are the ones that give you fits? Yes?
Can you look at 6?
Number 6, yes. So with any of these problems, and they can be applied to 1 through 6, through 7 through 12, you want to sit there and just read it. A cylinder, stop. What do we know about cylinders? Well, looks like a circle, another circle, and it's like this. It's got a height. It's got a radius. You know that the total surface area, I mean, just presenting knowledge, is 2 pi r squared plus 2 pi r h. We know that the volume of a cylinder is pi r squared h. And that's just from 2 words, a cylinder. A volume 2,000 gallons, stop. So volume is 2,000 gallons. It has a base of 200 square centimeters, stop. So the base, or the area, is 200 square centimeters. How high is the cylinder in feet? So one of the things that we need to do is just explore the understanding of what a cylinder is, and we've got geometry questions, we've got conversion questions. This pi r squared is the area of the circle and it is known as the base. So pi r squared is equal to 200 square centimeters. So we're getting information about this. Now, one of the things that we need to understand, and this is a good example about this, with physics problems, the first time you work on it, it looks like a mess. We're working in several different directions. Really, I mean, I don't have the solution in front of me. I'm doing this as you would do it. So the first time you do the problem, you just write it out and it looks horrendous. And then you rewrite it again and then you streamline it, make it look pretty. And you explore it and you poke it, and a lot of times it just doesn't work out quite right. And so you explore it in a different direction. Physics is about making mistakes, learning from them, and moving on. So I've got an area of 200 square centimeters. I got a volume. I need everything in feet. Maybe one of the things that I should do is change 2,000 gallons to cubic feet, just so I can get a number. So 2,000 gallons times 4 quarts per gallon times 946 milliliters per quart times, let's see, 1 cubic centimeter per milliliter. May not have been on the lecture, but that's how that conversion works. Next, 1 inch, 2.54 centimeters cubed. And then the last bit, since I can't write it right next to this, 1 foot per 12 inches. And then you got to cube that. So this converts gallons to quarts, quarts to milliliters, milliliters to cubic centimeters to cubic inches to cubic feet. And this is a number that I will want to, I will give that to you. 946 divided by 2.54 cubed times 12 cubed. And I get 267.26 cubic feet. So it's just a number that I need. Then the next thing is the area. I need to change 200 square centimeters into square feet. So a lot of times when you're faced with a particular problem, what you want to do is convert everything into the units that you want. So once again, 200 square centimeters, 1 inch, 2.54 centimeters, square it, times 1 foot per 12 inches squared, and then we get our answer, 200 divided by 2.54 squared, oh, not 1.54, 2.54 squared times 12 squared. 0.2153 square feet. Oop, not cubed, squared. Now I am writing the numbers out with a little bit more sig figs than normal, mostly because, yes, there is some rounding going on. And when you do rounding in the middle of a problem, you may want to give the number of sig figs a few extra digits. Mostly because with every time you're rounding, you're scraping off information. So we have the volume in cubic feet. We have the area in square feet, what is the height in feet? Well, volume is base times height. That is the area that we've been figuring out. So height is volume divided by base. So what you do is you take 267.26 divided by 0.2153. Feet cubed, feet squared, they cancel and you're left with just feet. And so that's it. Is it a big number? Yes. Do I particularly, am I interested in if it's a big number or a small number? No. What I am interested in is the technique that you use to get to it. That's the critical part. So it tested conversions, and basic geometry. Okay. So any more questions on this? Now, a lot of times, thinking as a student, when I was a student, students have a need for that simple, straightforward, linear process. With physics, it is not linear. It's more kind of a drunken stumble. Like the first time someone asks you, or the first time that they tell you, go to the square, you don't know where the square is, so you just kind of meander through the neighborhoods. And once you figure it out, you start making things more efficient. So the first time you do a problem, it's acceptable to just sit there and poke it, move around, and then eventually you'll start getting more efficient with it and it starts working out better. Next question. Yes?
Can we go with
Number 2. 25 cubic miles per years into gallons per second. So for number 2, well, at least you're amusing me with randomizing the problems. Some of the tutorials, it goes like this. What do you want to talk about? Number 1. Well, after we get done with 1, what next? Number 2. And it's just like, it just shows a little bit of lack of creative. Just keep me on my toes just a little bit. So for number 2, it is 25 cubic miles per year. And what I want is gallons per second. Now this is one of the brute force conversions that gets a little bit tedious. It's a little bit long to do the conversions. And what I need to do is attack it with quite a few ones. There are 5,280 feet per mile, and I need to cube it. I don't go from miles to meters. I go miles to feet, 12 inches per foot. I go then into 2.54 centimeters per inch cubit. I then go to 1 milliliter per cubic centimeter. I don't cube it because milliliter is a volume and cubic centimeter is a volume. I then multiply it by 1 quart per 946 milliliters, 1 gallon per 4 quarts. And so if you take 25 times 5280 cubed, 12 cubed, 2.54 cubed, and divide it by 946 times 4, you've converted cubic miles to gallons. It's going to be a big number. Well, I'm not sure if it's a big number or not. The denominator unit is in years. So 1 year, 365 days. You could use 365 and a quarter, it doesn't matter, as long as you don't cube or square this. 1 day, 24 hours. 1 hour, 60 minutes. 1 minute, 60 seconds. So this is all just one long conversion. And so if you take the numbers and write it all out and cube this, this, and this, but don't cube any of the others, it should be fine. So yes, it's on the high. I'm not going from square feet to square inches, a simple conversion like that. You could pull this off any of the conversions I give you on the test. Shouldn't be a problem.
So if we're going from like a distance to like a gallon or something like that, the volume, so we break it down into pretty much bring it down to a cubic into centimeters cubed, and then we can convert it into.
Yeah, 1 centimeter cubed is 1 milliliter. And so this particular thing right here is kind of is it really necessary? I mean, it's 1 cubic centimeter and 1 milliliter, but it does something important. It changes a linear cubed unit to a volume unit. So this is the main step right here. See, linear, linear, cubed, linear, linear, cubed, linear, linear, cubed, cubed, linear, volume. Don't cube it. And then everything else is either a volume to volume conversion or a time to time conversion. And you never square time in these units. Or at least I've never given a problem where it's necessary.
So you know that if you're going from a distance to a volume, you have to get it to the...
Yeah. The reason why you put a cube around it is because you're dealing with a linear unit, but in reality you're dealing with a volume unit. So to express linear units as volumes, you wrap them in a cube. But this is already wrapped in a cube, and that's a volume unit, so you no longer cube it. And it's for something like this, on the test, you're going to get something similar to this. You're going to have like an area over a time, a volume over a time, and you have to do a multiple conversion. Now, granted, it won't be in furlongs or fortnights. It will be conventional units. So handling number 2 should allow you to handle 1, 3, and 4. 4 is easy. 1 is easy. 2 and 3 are similar.
So can we do another one of those?
Which one?
Just one of the conversion ones.
Number 1. All right. So 3 feet. So we're dealing with an imperial unit and we're ending up with a metric unit. So feet to inches. Now comes the metric imperial conversion, 2.54 centimeters per inch. Now what I do is I'm going to convert it into meters. I mean, you can do centimeters to nanometers, but even I would kind of sit there and try to think it out and may get it wrong. So 1 meter per 100 centimeters, and then 1 times 10 to the 9th nanometers per meter. And that's number 1. Yes?
Sort of this is already asked, but anytime you start with cubed or square, you're pretty much going to be squaring every conversion?
Most of the conversions, yes.
Okay.
goes from feet, inches, centimeters to millimeters to nanometers? Is that what-
Feet, inches, centimeters, meters, and nanometers.
So once we get into centimeters, then we can switch over to the other metrics.
Yeah. I mean, I guess you could say 1 times 10 to the 7th nanometers per centimeter, but that's not something that I would know offhand. I would have to think it through. That's why I know this, and that. I just string them together. And with stuff like this, with conversions, you could do things slightly different, but the overall pattern is the same. Yes?
Is there like a overall conversion chart that you were recommending to memorize something that would help?
Probably in the notes. What I talked about. Because really, miles to feet, feet to inches, inches to centimeters, centimeters to meters, meters to whatever metric thing you need. I've gone over pretty much everything on that list that I wrote out. If I didn't mention that unit, unless I could say, I'd know that. 4 quarts to a gallon, but everybody knows that.
What about the milliliters to a quart?
940, yeah. If I have not written that down, 946 milliliters is a quart. Add that for sure. Because that milliliters leads to quarts, quarts lead to gallons. And gallon is typically a unit of volume for the imperial system. I would say that the list that I gave probably sums it up best, most efficiently. Just gives you the straight up conversions and that's it. I mean, I'll give you the conversion of centimeters to inches on the test and maybe feet to miles, but I won't give you inches to feet. I mean, I give you some credit to knowing the basics. The 946 to quarts is a little unusual, but 4 quarts to gallon, I give you this, but the 4 quarts to gallon, I'm not. So a lot of the basic conversions will be on the test. How you work with them, well, it's up to you. Next question. Yes?
On number 2, after you did 1 year, 365 days, did you skip one of the conversion steps? You said 1 year, 365 days. And then
Well, this year cancels with that year. So now I have days.
okay.
Days cancels with days. Yeah.
Have we done number 3 yet?
No, we have not done number 3. Would you like for us to do number 3?
Yes, sir.
Okay. I know full well we're going to do all of this, so So we have 10 meters per second, and we need to change it to furlongs per fortnight. So we could either start converting the lengths or the time first. It doesn't matter. So I need to convert seconds to minutes. Minutes to hours. Hours to days. Days, 14 days per fortnight. So this is really the only time the whole semester we're going to be playing with furlongs per fortnight. We won't have this on the test, but it's more important to understand how to convert. Now seconds have been canceled out, and what we're left with is fortnights. Now we have to change meters to furlongs. So I continue to multiply 100 centimeters per meter, 1 inch, 2.54 centimeters, 1 foot, 12 inches, feet, miles, 1 mile, 5,280 feet, and then 8 furlongs per mile. So we're left with furlongs per fortnight. And since we're not dealing with areas or volumes, nothing is squared in any of this. So really the only thing that we have left of this is number 5. Do we want to see number 5?
Sure, let's go for it.
Okay, let's go for it. So for number 5, sphere of radius 2 meters into cubic inches. This is one where my original intent was to get the volume of a sphere in cubic meters and then convert it to cubic inches. I mean, that's a way that you can do it. How many cubic meters in for a sphere? 4/3 pi r cubed. And you could do it that way. But then it involves a lot of converting where you need cubes. But now, someone came to me and said, is this legit? And I looked at it and I said, yeah, you changed 2 meters into inches. So 2 meters, 100 centimeters per meter, to 1 inch, 2.54 centimeters, and that's what I need. So this will be the new radius, and the volume, which will now be in cubic inches, is just 4/3 pi r cubed, where that r is in there. So the easiest part, or the easier way to do this, is meters to centimeters, centimeters to inches, and then take that answer, which is your new radius, expressed in inches, plug it into the volume equation. Now you got cubic inches. That's it. Yes?
Is there point one?
Is there a what?
Is that point one or just 1?
1. There's no point. So we've done 1 through 6. Now for 7, we got to remember the map for Mississippi. The numbers may have been a little bit different than earlier lectures. Memphis is 300. State line is 0. Jackson is 150. I believe in lecture I said Oxford was 175. Yeah. If you use 175, that's great. If you use 225, which was used in earlier versions of this map, that works too, but we'll use 175. What is the displacement from Memphis to Jackson? So displacement is just delta x. This is our x-axis. We choose the origin to be state line. And displacement is the final position minus the initial position. So the final position, which is in Jackson, is 150. The initial position is 300. And displacement can be negative. What is the distance from Memphis to Jackson? Well, distance is just the absolute value of displacement. So it is the absolute value of 150 minus 300. I'll leave a little bit of mystery to you. You can figure it out. If it took 2.5 hours to drive from Memphis to Jackson, what's the car's velocity and average speed? Give answer in miles per hour. Well, velocity, the average velocity, is the displacement over the change in time. The change in time is 2.5. This displacement is whatever you get from there. Velocity, average velocity, can be negative. Speed, average speed, is the absolute value of average velocity. So take the absolute answer or absolute value for what you get here, and then you have the absolute speed. Or average speed. And so that's number 7.
Where did the 2.5 come from?
2.5 came from the fact that it said if it took 2.5 hours to drive, so I guess that does need to be one of the things that all students, including the professor, must do. Read the whole thing. Granted, it would be delicious on the first line of the test say, read all instructions, and then the last line of the test be, it's a take-home test, you can go home when you want, and then see how long it would take for people to figure it out. But I'm not going to do that. It would be evil. I would love it. It would be nice. Actually, you wouldn't want, to be honest, you would not want a take-home exam because it changes the parameters of how the test is given. A test is an hour 15 minutes, an hour 15 minutes long. So I have to make the test fit within those boundaries. If it's a take-home test, I've got a week. Oh, we could have that. And I understand, I'm not an idiot. Yes, we operate under the Ole Miss Creed. Yes, I could obligate you to say, I promise I won't talk to anybody else about the test. But I'm a realist. So I realize that not only am I testing you, I'm testing your tutor as well. So I would throw nightmares at you. So let's not do that. Walmart is 1.2 miles away. What average speed will your car be traveling if the journey was made in 12 minutes? Give answer in miles per hour. So you take that time and it is 0.2 hours for the total time. The average speed is the absolute value of displacement over change in time, or 1.2 over 0.2. You're going pretty slow, but it is West Jackson on a Friday afternoon. That's the first problem. Second part of the problem, if your average speed was 12 meters per second, so stop, average speed, 12 meters per second. How long would it take for you to get to Walmart? Give answer in minutes. So what we want to do first is change our speed from meters per second to miles per minute. We could do that. We could do all sorts of conversions. 60 seconds per minute. 100 centimeters per meter, 1 inch per 2.54 centimeters, 1 foot per 12 inches, 1 mile per 5,280 feet. And that will give you your average speed in miles per minute. Now, average speed is the displacement, or I'm sorry, distance divided by the time. Or you could say time is the total distance divided by your average speed. The average speed is the value that comes out of this. The distance, 1.2 miles. The distance is in miles. The speed is in miles per minute. You're left with minutes in the numerator. And that's all you would have to do for that part of 8. All right, so number 9. Number 9 is a one-dimensional motion problem. A car is traveling 80 meters per second from left to right when the brakes are applied. Stop. We've got a car. This is a picture of my car. Don't make fun of my car. This is not art class. It's traveling 80 meters per second when the brakes are applied. So that means what is 80 meters per second? Velocity. More important, it is blank velocity. What is blank? Initial. Good. So it's V sub naught. After 15 seconds, it comes to a stop. So it's moving over here. The car is here. Its final velocity is 0. And because that's what it means when you say come to a stop. The time that it takes to do this is 15 seconds. How far did it travel before it came to a stop? So really, it wants that. Since it's a one-dimensional motion problem, you say most usually, or frequently, you pick the initial position of the car to be the origin. Also, it's traveling from left to right. Pick the leftmost part and say that's the origin. So that's 0. That is whatever x is. It's a one-dimensional motion problem. Let's see what we could do with this. X equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. Before we really ask ourselves about what do we know and what do we don't know, let's ask this. Which parts are 0? The origin is 0. The final velocity is 0. Now we look at what we know and don't know. I know time. I know initial velocity. But I don't know A, and I don't know X. So on the left is one equation with 2 unknowns. On the right is one equation with 1 unknown. Remember what we've talked about on yesterday. Establish your origin. Establish your directions, positive to the right, negative to the left. Write down what equations you think may be used. Identify what you know and don't know. See if one of the equations breaks down because it only has one unknown. That's the one we attack first. Minus V naught AT minus V naught over T is equal to A. Minus V naught minus 80 T 15. 80 divided by 15 is something and change. 5 1/3. Negative 5.33 repeat meters per second squared. Now, should we have a value of A that's negative? Does that make sense? Yes, because it's slowing down. When objects slow down and this thing is moving to the right, if it's slowing down, the acceleration should point to the left. If it's sped up, the acceleration vector would be in the same way as the velocity vector. Slow down, opposite. Accelerate, same direction. Now A becomes a known quantity. So X can be determined, V naught 80, T 15, plus 1/2, negative 5.333, close enough, and then 15 squared. Fortunately, I still have that number in my calculator, so let's go use that. So 600. Okay. So that's everything that we need to know in terms of the first question. Second question, what is the magnitude and direction of the car's velocity at 10 seconds? Well, now the time is 10 seconds. In the initial question, we were going from 0 time to 15. Now we're going from 0 to 10. The one thing that is consistent between the two problems is that we now know what value. At the beginning of the problem, what didn't we know? Now, what do we know? We know the acceleration. Granted, we know the total distance it moved, but that's not necessary for this part of the problem. The acceleration is. Because the acceleration at the beginning of the problem is negative 5.33. At the end of the problem, it is that value, and in the middle, it's still negative 5.33. So V naught plus AT, V naught 80, A, negative 5.33333 forever, and then 10. And that's it for that question. Oh, what is the magnitude and direction of the acceleration? So the magnitude of the acceleration is just absolute value. Because it's negative, you say it's to the left. So you could say either negative 5.33 meters per second, or you could say 5.33 meters per second to the left. Either one would be acceptable. And also it brings up an important just comment of the way that part of my teaching philosophy is these problems I created or heavily borrowed from other sources. The way that I ask my problems are definitely non-linear. Like, I don't ask the questions and arrange them in the paragraph so that you know that you have to deal with question 1 first, and question 2 second, and question 3 third. Sometimes What did we do in this particular problem? Well, first of all, we didn't read the whole problem. But the third question is, what is the magnitude and direction of the acceleration? What did I do first? I answered what the acceleration was. You need to be prepared to be given problems where the first question isn't always the first one you should answer. In fact, it's one of the styles that I've kind of adopted from MCAT preparation, because MCATs don't do that either.
Where did you get the 10 seconds from on the AT, negative 5.33 times 10?
The 10 came from reading the second question. What is the magnitude and direction
Oh, I see.
of the car's velocity? Yes, at 10 seconds. So yes. So answer, read the question.
Thank you.
You're welcome. In the back, in red.
What are the units of magnitude?
Well, when I say magnitude, it's the absolute value. So if my acceleration was negative 5.33 meters per second, the magnitude of that acceleration is 5.33 meters per second. So magnitude is just implying just the value itself with no signs, no information regarding left or right. This is acceleration with a negative sign. If you don't see an absolute value running around inside, you know that if the acceleration is negative, it's to the left. If it's positive, it's to the right. If I say magnitude of acceleration is 5.33, I give no information about direction, at which point you have to ask, well, is it going left or right? Answer, A was originally negative before we took the absolute value of it, so it has to be left. So 5.33 meters per second to the left. Magnitude doesn't deal with units, it just deals with what that number is. Does that answer?
So for the second question, or what is the magnitude and direction of the car's velocity at 10 seconds, would this be whatever the answer is to the left? Or is it meters?
Well, that's an interesting, you know what, I haven't gotten, what is 80 plus negative 5.333 times 10?
I got 26.6.
26, okay. Did you get negative 26 or positive 26? Positive 26. So the magnitude is also positive 26. Because the answer that you got was positive, the car is heading at 10 seconds to the left or right? To the left?
To the right.
Oh, to the right. Correct. Why? Because it was positive.
Okay, so the answer for that was
Mhm.
26.
Yeah.
Okay.
I do wander out into the audience sometimes. I don't think this is a barrier, a wall. So questions about this? Yes.
Is there a certain way, like, some teachers are picky how we present our answers on our page? Like, do you want us to box our answers? Like,
I would say that it is a great, the graders are quite well versed in the diversity of types of answers that the students get. I would say that a grader who isn't confused is a happy grader. So I understand when I'm doing this, it's kind of sloppy, but there is kind of a method to the madness. We're fine with that. If it looks like your 4-year-old niece wrote it, they're going to get upset. So that's why I mentioned earlier in lecture, I love like colored pens, colored papers. It never hurts to add commentary to it. And speaking just as a former grader, if you have an answer and it's boxed, and let's say the answer is like 4.0 and you have 3.99 or 4.01, I look at that and go, I've got 475 tests to grade. I need to move quickly. So when I see the right answer in the box, I tend to move on. So if you don't have a box, I'm fine with it. Having it in a box makes it my job way more easier. And happier and better dexterity, and a happy grader is more willing to give out more points. So. All right. Mm-hmm.
Speaking of grading, is there like any partial credit?
Yes. There will be partial credit in the test. So much of physics is based on, do you understand what's going on? Can you set up the test problem correctly? That has value. Can you proceed with some basic stuff to let us know that you know what you're doing? Yes. Are we going to take a full 15 points out of 15 because you dropped a minus sign at the very end? No, but we will tag you for like 2-3 points. You will never get what the math department calls a box test, which is you could do the right thing, write the solution perfectly, put the incorrect answer in the box, and they take away all of it. I think that's rude, and I think it's inappropriate. So we do give partial credit, yes. But I will say this: the graders are looking for students who are trying to scam their way into points, and we'll talk about that more as the semester progresses. Yeah. Apparently, people are just dropping calculators. I pick a number that tries to predict the number of dropped calculators during a test. And then I make a bet. So, that's what keep me amused during tests. Any other questions about this problem?
How specific do you want like the graphs to get like that on them? Like,
I would expect like dead on, because
or do you like if they're just kind of sketch?
general shape sketch.
Okay.
As in, sketch the plots of position, velocity, and acceleration. So with acceleration is always constant. It was always negative 5.33 meters per second. So a line that looks like that is okay. Velocity starts positive and goes to 0. It's a linear line because v is equal to v naught plus at. That a is the slope of the line, which is negative 5.33. The position, it looks like this. At the beginning, it has a high velocity, so the slope is large. With time, the velocity goes to 0, so the slope should flatten out to 0. And that's what we want. This would be incorrect, because this type of slope, like this, implies that the slope of the line is getting greater or speeding up. So.
That right there is acceptable. You don't have to do anything like
I'd be fine with this. In fact, yeah. I'm realizing we're down to 33 minutes, so I'm trying to... What I'm going to do now, 10 is pretty straightforward. For number 10, think of, what I may end up doing, 10 I can kind of maybe do during class. But for 11 and 12, I do want to talk about them. So you can buy. I mean, this will be online in an hour or two anyway. You're welcome. All right, what we're going to do is I'll do number 12 first. So a monkey on a 100-meter high 100-meter high tree, super monkey drops the banana. And then 2 seconds later, she realizes she wants it back. So really, we have a banana that is dropped, and then before it hits the ground, in fact, the distance before it hits the ground is 15 meters. So at the top, the banana is released, it falls a particular distance. At 15 meters above the ground, the monkey picks it up. In this type of problem, we got to first figure out what we're dealing with. We're dealing with a one-dimensional motion problem. We're dealing with a problem that looks eerily similar to the Justin Bieber Velociraptor problem, where 2 objects are moving and eventually catch up with each other. If I simply asked you to drop a banana and it moves 85 meters, you could answer quite a few bits of information from this, such as, well, let's deal with the basics. I'm going to choose the origin to be the top of the tree. And I'm going to choose up as negative and down as positive. And why is that? Because everything is moving down. The banana is moving down, it's accelerating down, its velocity is down, its position is down beneath the top of the tree. Super Monkey is going to have the same thing. So for the banana, x equals x naught plus v naught t plus 1/2 at squared. What do we know about x naught? It's 0 because it starts at the origin. Why? Because we said that the beginning of the point was the origin.
So it's not always going to be origin?
Not always. In this case, it is. So that's the answer. The initial velocity is 0. The initial velocity of the banana is 0. Why? Because it was dropped. Dropped means that the moment you let go of an object, the moment I've let go, it's just suspended in air. And then it's now under the full influence of gravity and it starts accelerating. So drop means velocity is 0. I know I'm on the planet Earth, that's A. I know that x is 85. If the distance from there to there is 100, and the distance from there to there is 15, if that's the origin, then the coordinate at that point must be 85. The only unknown is t. So 2x divided by a is t squared, and the square root of 2x over a is equal to t. So 2 times 85 times 10, not negative 10. Why? Because down is positive in this case. So 4.123 seconds. That was the time that it took for the banana to fall to where it got to when it was caught. So if the banana fell for 4.123 seconds and Super Monkey waited 2 seconds to go after the banana, what is the flight time of Super Monkey? So at time equals 0, the banana was dropped. At 2 seconds, Super Monkey realized that she wanted her banana back. And at 4.123 seconds, the banana was caught, which means that she has only 4.123 minus 2 seconds of time to go after it. So the time for the monkey the time that we have for the monkey to catch the banana is 2.123 seconds. You have to consider the fact that she waited. So the question is, if Super Monkey can accelerate at 2 times that of gravity, so for those of you at home, this is the problem. If Super Monkey can accelerate at 2 times that of gravity, what is her initial velocity so that she catches the banana 15 meters off the ground? For how long was the banana falling? We just answered that. So we have to find the initial velocity of the monkey. So she sees the banana and just hurls herself after the banana. So x equals x naught plus v naught t plus 1/2 at squared. I do know what the value of x naught is. It's 0. I do know what the value of x is. That's the catch point, or 85. I do know what time is for this, 2.123 seconds. And I do know what A is. A is positive 20 meters per second per second. She can accelerate at twice that of gravity. So 10 times 2, or 20. Physics 213 gravity magnitude is 10 meters per second per second. We don't deal with that 9.81 stuff. So solve for V naught. That's the only unknown in the problem. So solving for V naught, x minus 1/2 at squared is equal to V naught t. Divide both sides by t, x over t minus 1/2 at is equal to V naught. X divided by t is this, 1/2 at squared divided by t is this. And then we plug everything in. 85, 2.123 minus 1/2, 20, 2.123, and that's V naught. And then that's the answer.
Where did you get, the acceleration? Does that say positive 20?
Mm-hmm.
What's, I don't.
Okay. In the problem, once again, the advice is read the question. In sentence 3, if Super Monkey can accelerate at 2 times that of gravity, so her acceleration is 2 times 10, or 20. And so that's where the 20 comes from. Yes?
Why did you not divide the whole side by t? You just did.
I did divide the whole side by t. Actually, let me do intermediate steps that really describes what goes through this. X minus 1/2 at squared divided by t is equal to V naught.
I can understand that.
Yeah.
I got it.
Yeah, there was, I will say this, what you have just asked is appropriate.
I forgot about the square.
Yes, thank you. And I get students, and I am with them, who are very frustrated when professors go, it could be easily seen that, and what you get is a 10-step thing that he just jumps and hand waves through. For this, when I went from there to there, I magically divided everything by a factor of t. And so it's,
I just didn't pay attention to the square.
yeah. And so that's the super monkey problem. All right, we got, after this problem, this one is done. We really won't have time for 10. So we'll either think about it on Tuesday or, I mean, it's a 1D motion problem. Also, if I have the time over the weekend or on Monday, I'll post old tutorials from previous semesters, and so you can look at that stuff, and frequently I do the same problems. Number 11. You're in a, so this is the beginning of 11. Your office is in a multiple-story building. It has a glass window 2 meters high. So there are 2 points in the room that are important. Top of window, bottom of window, and they're not written to scale. The difference between the two is 2 meters. The distance from the bottom of the window to the street, 75 meters. Now, granted, this problem is, in my opinion, the toughest of the 1D motion problems that you're going to deal with. It takes 0.1 second for her, Taylor Swift, to pass from the top of the window to the bottom of the window. So the time at the top to the time at the bottom is 0.1 second. Now, if her initial velocity was 0, which means she was dropped, so there is a drop point. From how far above the top of the window did she begin her fall? Which is the question, what is that distance right there? And this is a problem where really I want to read the whole problem before we start working on this. For how long was she falling when she reached the bottom of the window? So I want to know this time here. Now there are, okay, I need to know that time. I'll talk more in just a second. What was the total flight time from the beginning of the drop until she reached the bottom? So I want to know that time. What was her final velocity the moment before impact? So I want to know that velocity. And once again, let's reread this. If her initial velocity was 0, from how far above the top of the window, I need to know this. For how long was she falling when she went from there to there? Yes. What was the total flight time? There to there? Yes. What was the velocity at impact? That V right there. Okay. So symbolically, we've kind of drawn everything out. There are 4 points for consideration in this problem. And I will call them A, B, C, and D. Now D is obvious. D is at the street level. C is at the bottom of the window. B is at the top of the window. And A is when she began her fall. Everything is down. Gravity is down. Her motion is down. So what we're going to do is we're going to set the origin to be at the top of the building. So the initial position for the whole problem is 0, which means this coordinate is the height x, which means this coordinate is x plus 2, and this coordinate is x plus 2 plus 75. But we don't know x, but we're going to figure it out. Now this is a lot like a Sudoku puzzle. You've all tried Sudoku puzzles. You don't start with the places in the puzzle where you know nothing about what's going on. You start in the points where you can kind of line everything up and figure things out. The most amount of information we have here is this. We know the total time it took for her to fall from the top to the bottom. And we knew that distance. So let's just study B to C. Well, it's a one-dimensional motion problem. So we have x equals x naught plus v naught t plus 1/2 at squared. And we have v is equal to v naught plus at. Identify what we know and what we don't know. Now, I'm a little unclear about the velocities. I know nothing about the velocities. I do know, however, that I am on the planet Earth. So that should be positive 10 meters per second squared. And I know what the time is. I know the time is 0.1 seconds. I know what x is, the initial position, or I know the initial position, which will be what I call x. The bottom of the window, the final position, so these x's aren't really the same. The final position is x plus 2 plus v naught t plus 1/2 at squared. Now in this particular part, I don't know the final or initial velocity. I have two unknowns, so we avoid that equation. Here I know the initial position, this weird, bizarre position x that we don't know. Here I know the final position, x plus 2. So x naught becomes this variable x, x final becomes this final, or this mystery position x plus 2. I don't know this, or this, but I do know that, obviously, this, and this. So awesome, I've got a v and an unknown v naught on the right, and I have an unknown x and v naught on the left. Why should I not stress out? And you're just looking at me like, oh, I don't know, we're all doomed. So we're doomed. Into the problem. What happens to the x value in that equation? I have no knowledge of x, but I do know one thing about x. I got an x on that side, an x on that side. I'll subtract both sides with x, and they go away. Now I have one equation with one unknown. Now I can determine what v naught is. So 2 minus 1/2 at squared is equal to V naught T. And like we did before, I'm going to divide both sides by T, which means 2 divided by T is 2 divided by T. And 1/2 AT squared divided by T is 1/2 AT. And that is equal to V naught. So 2 divided by 0.1 minus 1/2, 10, 0.1 is equal to V naught. Now, I love plugging in numbers and using 10 because so much of this stuff cancels. I'm left with 20 minus 1/2, so 19.5 meters per second. I now know this is the velocity at point B. So much of this is just exploring it. With this basic knowledge of one-dimensional motion, I've been able to extract a value, the velocity at point B, which is the initial velocity of B to C. And this is the key statement for the whole problem. The initial velocity from B to C is the final velocity from A to B. So let's just, okay, so the velocity at B when you're going from B to C is 19.5 meters per second. So now this is the question, the dumb question that you should go, how dare you ask me such a question? I'm already looking. So if we know that the velocity initially going from B to C is 19.5 meters per second, what is the final velocity of Taylor Swift when you go from A to B? 19.5. Yes. And you should be a little bit, just a slightly bit, insulted that I would ask such a dumb question. Because you're smart. You're getting it together. Okay. So you've got to make that connection. The final velocity from A to B is the same as the initial velocity from B to C. Now that you know the final velocity from A to B, you know that she was dropped. You know that her initial velocity was 0. So let's talk about A to B. She was initially dropped, which means the initial velocity from A to B is 0. The final velocity, the velocity at B, is 19.5. She's on the planet Earth. A is 10. The only unknown is T. The time from A to B. So V divided by A is T. So 19.5 divided by 10 is 1.95 seconds. That's the time that it took for her to fall from the A to B. Which means that the time that it took for her to fall from A to C, which is this, is 1.95 plus 0.1, or 2.05 seconds. So we've answered one of the problems. Like a Sudoku puzzle, you start answering blocks, and eventually blocks start multiplying in terms of the ease of its answerability. Now that you know the time that it took for her to fall from A to B, you can easily calculate that distance, x equals x naught. Well, that's the origin of the whole problem, or 0. Plus v naught t, she was initially dropped, so that's 0 as well. Plus 1/2 at squared. 1/2 a 10 t 1.95 squared. So the total distance that she fell from A to B, which is that question right there, (19.0125 meters. That's the total height or change in altitude from the top of the building to the top of the window. Yes, this is a big difference from calculating distances and displacements from Memphis to Jackson. This is now, we're starting to, the more tools we have, the more complex questions we can answer. So the total time from the top to C is known. The total distance from A to B is known, which means now we know the height of the whole building. The total height of the whole building is 19.0125 plus 2 plus 75, or 79 plus 19.0125. So that's the total height of the building. Well, what is the use of that? If I, like the banana drop problem, if I told you to drop a banana from 96.0125 meters, how long would it take for it to drop that far? You could answer that. X equals x naught, which is 0, because it starts at the origin, plus v naught t, it was dropped, that's 0, plus 1/2 at squared. A and x are known, t is unknown. 2x over a is t squared, or t is the square root of 2x over a. X is 96.0125. Multiply by 2, divide by 10, take the square root. I leave it to you to solve. The final velocity is v naught plus at. V naught is 0, a is 10, t is whatever that t is. Everything that we have done today has been based on using two fundamental equations. X equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. We have used them in a variety of ways based on what we know and what we don't know. Now, granted, initially, this is the reason why I assigned this problem is to just have you look at it, freak out, and then show you how problem solvers work. Many times, I love looking at a problem and just saying, I have no clue how to do this. But what you do have, what I have, well, I'm still developing, and what you're going to develop soon, is a sense of problem solving. That technique to solve this problem is way more important than actually knowing specifically what to do in this problem, or the answers. The answers are irrelevant. It's the procedure that I want you guys to know. We'll talk more on Tuesday. Have fun in lab on Monday. That's it.